Hello, how's it going? In this video, we're going to start looking at lighting. Just bring this up. What's the concept of lighting? I'm feeling lazy today. It's winter. I'm not going to pull out extra equipment and anyway. So here is how the idea works. Let's say we have some sort of light, a light source of some sort, and then we have an object. I know. So the goal is to say, hey, for a given fragment, does that trace directly to the light? And what we will have is we'll have a bunch of other objects. And yeah, let's say there's one behind the light. Okay. So what we want to do is we want to go, okay, we know that we're lighting this fragment here, and we know that we are considering this light here. What is the distance between those two? And that's perfectly fine. We can get that straight away because we know two positions in space. And then the second question is, for each of these objects, what is the distance to them along this ray? And for these objects here, the answer is it's unsolvable. So I'll put some crazy high distance like 999, who cares? Okay, for this object here, there is a distance, and the distance to that object is greater than the distance to the light, which means we do not have to consider that. On the other hand, if we put another object here, then the distance to this object would be less than the distance to the light along the same plane, which indicates that this light has been blocked, and lighting calculations from this light here would not be applied to this fragment. So this fragment would be in shadow from the perspective of this light. However, if we had another light over here, then this one would be lighting this shadow, this thing here. So this fragment would be, have some green calculation, and then if I sort of calculate, I know it's not. Okay, so there'd be some region where the red light would not have an influence, but everywhere else it's sort of, there would be some red light coming. Oh, that was a yellow one. Anyway, who cares? You get the idea. The point still stands. Anyway, so how do we implement this? Well, we will start at the simplest level, and then we'll kind of ratchet it up from there. So we'll start with declaring a light class, and yeah, it'll be very straightforward. We'll just go ahead and code this up now. Okay, great. We have that light class up there. I was just thinking, do we need this config? Yes, we do, because we're calling NumPy functions. Okay, that's fine. Now go to our scene, and we can add a bunch of lights. And I'm also going to tweak this scene a little bit, just because I found that the spheres are a little separate from the planes. I want to kind of bring them together, tighten it up a bit. So let me just go with this. These planes, if we look at this math here, are going between 0 and 2 in the x and y, and they're at -1 on the z. So I'm just going to, for the centers, we'll go between 0. Let's you know what? Let's spread it out a little bit from 0 to 2. So, okay, 1, 2, 3, that's fine. Why am I talking to myself? And I'm going to bring them down, up and down. That's fine. Okay. All right, maximum radius, I'm going to bring that down because now that they're coming closer to the plane, I don't want them to be like dwarfing it. Yeah, this is all fine. Okay, so I'm just going to make a set of lights. And I'm just going to copy paste the sphere. Oh yeah, of course we need to import that. Yep, so instead of center, that's going to be position. And I guess that's probably fine. Yeah, why not? We'll see how it goes. It doesn't have a radius. It does have a color. That's probably fine. And we'll go with strength. And for the strength of the light, I want it to be maybe between 1 and 2. No, I just changed my mind. 1 and 3. So a strength of 1 will be sort of no attenuation or magnification. And yeah, because of the distance fall off, I'm going to be pretty liberal with the strength. We can probably dial that up quite a bit. Okay, and the rest of this is fine. So we'll go to the engine. And now in the engine, we need to sort of update a few things. So I'm going to go to the resource memory. And remember, the resource memory is where we allocate space for 1024 objects. So spheres plus planes. And I'm also going to now include lights. I don't need to actually do anything in this function, but I've been finding that it's a really great place to keep my scheme up to date. So later on when I go to unpack objects, I can refer back to this and say, this is how my memory is packed out. Okay, so we can see the first pixel will have the red, green, blue, and the strength. And then the second pixel will have, the X, Y, Z and the strength. Yeah, okay, now I'm just going to be pedantic for a second, just bear with me. That's probably fine. Okay, so again, like I said, I don't need to do anything here. This is just allocating the memory, but I do find that it's useful to have the scheme documented here. Okay, what we do need to do is down here, record sphere, okay, record plane, okay. Now I'm going to record a light. So I'm going to make a record light function. Okay, hopefully that makes sense. We're just recording it in the same layout that we had above. Now this recording will be done in the update scene function. So we'll go down to the update scene function. And the first thing we do before we record a bunch of objects is we send in the number of those objects. So we're going to go call this light count. Going to go number of lights that we have, and then so loop through our lights, and we'll record that light. Okay, now note that first of all we recorded all the spheres, and then when we went to record each plane, we added onto the loop variable, we added on the number of spheres which had already been recorded. This makes sure that the next plane that I record is not overwriting a sphere, because we have objects of different types sort of written to the same image, the same buffer. So what I'll do is I'll also add the length of basically the number of planes in my scene, and that'll make sure that I'm recording the spheres, the planes, and then the lights. Okay, but this should be fine. So now I'm going to head to the shader, and now everything's sort of going to get a little bit more complicated. I don't want to speak you out too much, but it is going to get a little bit more complicated. So again, we'll try to sort of take it one step at a time. The first thing we'll need is we'll need a structure for our light, and then we'll need a bunch of function declarations. So just kind of take it off. So we'll go okay, that's that. Now we will also need an unpack function and a light count. So down below we'll go uniform float light count. That's looking good. And then right down the bottom we have, where are we? Unpack plane. Okay, we'll also go unpack light. Stick those together. Stick these together. Okay, good. Now for the light, the lighting specific functions. So what we sort of want is we want given a render state, because the ray has already traced and it's done its thing and it's hit something. We know the position it hit. We know the normal of that fragment and everything. Basically, we want to return a color in vec3 form, which we get by lighting that fragment. And all we need is the render state that was hit. And then what are the subsets of that? Well, we will need to get the distance. We'll need to get the distance to each of those objects. So just like we have a hit function, I'm going to make a... Because essentially the distance to function will be a simplification of the hit function. It traces a ray out from a point, but then if there's a hit, then it just returns the distance instead of all the other information. So I'm just going to call this so just for a given ray and a given target, what's the distance to that target? Now we'll sort of start to think about how we're going to set things up. If I look down below, then what I'm doing is I'm starting with a, if I hit nothing at all, it'll be white. And that's the reason that the sky is white. So for instance, if I set this, just as a little side note, oh yeah, rookie error. For some reason I made this when I was, made the same error when I was, okay, fingers crossed I haven't goofed the rest of this up. So as we can see, we have a sort of default of, we have a sort of default of orange because I set that data in, but there's a side effect that also, if a ray hits the wall and then it bounces, it's going to hit nothing a lot of the time because this is an open scene, this is an open environment. So it will sample that sky color. And that's an issue. Now, it's something that we kind of had to do, because otherwise we would have recursive functions, which shaders are not allowed to do recursion. It's too complicated. So instead, we sort of put this into this big multiplicative loop where every time we step through the loop, we sort of multiply the ray with the next thing that it hits. And that's a problem. That's a problem. So I'm actually going to kind of calcify this tracing path a little bit by calling discrete functions. So we'll have a function for the first initial trace, and then we'll have a function for the next trace and the next trace and so on. It's a little bit janky, but at least it works. Okay. So having said all that, I'm going to have to sort of change all of this. Okay, so if I wanted to put more bounces, I would put more functions. The reason that I'm also taking in the pixel coordinates, the coordinate of the screen, and the size of the screen is in order to generate random noise that will be used in setting up the next bounce. And that's the reason why I don't need that information in the final pass. But okay, so what I'll do is just sort of get this out of the way a little bit, and we'll set up for the first pass. So the first pass is essentially going to do this. So we can sort of grab all of that, get rid of this, and we can say pixel equals first pass. All of that stuff. Okay, so again, we get a render state by tracing the ray, which we're given. Early exit. Well, what we'll do is we'll return a value. So we'll say put in a black pixel. The reason I'm doing this is I want to make this more physically realistic, which means I want to have a black sky and be lighting things up, basically. So, all right, if we don't hit anything, then just return the pixel, which should be black. In other words, that's the sky color. Now, if we did hit something, then, yep. Unpack that. Actually, we don't need that, do we? That's fine. I changed my mind. Okay, now we're not going to multiply this with the pixel. That is a mistake, because the pixel starts off as black. Like I said, we're not doing a multiplicative thing. That's not how we're doing our recursion. Here we're doing the recursion by simpler means, by hard-coded functions. It's acceptable. Now, the only other thing I noticed is I'm passing in a bounce parameter in order to always be sampling a different part of the random noise texture. But now I'll hard code that to 0 because we're on the initial trace. That's fine. All right. Now, what was I doing? Okay, so let's just do this for now. Let's just go return pixel. Okay, we're just going to worry about the first trace. Well, that's strange. Wasn't doing that before. Huh. Interesting. But yeah, the sky's not black. I think, let me just check this again. If I go to the trace function, it might be here as well. Let's set that default to black and see what's happening. So again, I want the sky to be black, and I want the objects to be their regular color. because this will make the lighting look more realistic. I gotta say that is very cool, but it definitely shouldn't be doing that. So let me just... That is cool though. Let me just check my notes. Oh, yeah, this is a problem, right? Don't just say pixel, actually, and the function. Return the pixel. Right, so in cases where it's hitting the sky, it's trying to sort of continue or something. Trying to bounce off of... So it shoots out, it hits nothing, and then it tries to reflect off of nothing, which is making that weird noise. That's better. It's nice, and it's stable. So before we worry about reflections or anything, let's try to get lighting working on this scene. So what I want to do is I want to grab the color of the render state and I want to multiply that with the lighting result. Okay, so I'll jump to the light fragment section. Now I'll just start off by adding an ambient component. And this ambient component will be sort of returned at the end. And then we'll have a loop in here where we go through each of the lights and we add a contribution from each of the lights. So we'll say, okay, so this is going for each of the lights. Again, if you think about the layout there, because yeah, the lights are in that block which goes beyond the spheres and the planes and up to those. Okay, right, so what I'm going to do is I'm going to say, okay, go make a variable to indicate whether this this light is blocked from the thing or not. Okay, so this is a good point to write our unpack light function. It's going to be very similar to unpack sphere. Annoying. Okay. Okay, yep, I think this is fine. So just sort of grabbing those by accessing the image and we'll, yeah, great. Okay, so let's say we have a given light. We know its position, its color, and how strong it is. Then the next thing we want to do is we want to work out whether that, well, just work out a bunch of directions. So let's work out the direction from the fragment to the light. That will be the light's position minus the fragment's position, and the fragment's position is stored within render state. Okay, then we want to get the distance to the light, and we can get that by taking the length of that direction vector. Okay. Now what I'm going to do is I'm going to set up a ray which traces from the fragment to the light. And then I'm going to need to look through all the spheres and planes. So then the question is, if that trial distance is less than the distance to the light. And if that's true, then we'll set our blocked variable. Then we'll do exactly the same thing for the planes. Okay, that's fine. And then let's say we've done all the spheres and all the planes. We want to check, are we blocked by anything? So we'll say if not. And I'm just going to go with something super simple right now. I'll say color. So right now I don't care about distance or anything. I just want to indicate which fragments are in light and which ones are in shadow. Fingers crossed. Oh, what am I thinking? I haven't written the distance to functions yet. Okay, so let's uncross the fingers and let's have a look at these. What I can do is basically grab the hit functions and copy paste them. Okay, then we're going to apply liberal simplification. The programmer's scalpel, if you will. This stuff is all fine. So let's say we inside here, I'm actually going to return what I want. Outside, if we go through and basically the equation's unsolvable, I'll just return a really large distance, so it obviously won't interfere with the light. Now, inside here, I get the t, and this is super important. This is super important. T needs to be above a certain threshold. Otherwise, we could have spheres which are blocking lights because they're kind of behind our render target. You know what I mean? So a positive T means that the sphere will be in front of the render target because it's tracing outwards from the fragment towards the light. A negative T will mean the sphere is behind the render target. So we only want to worry about this if we've got that. So if we get our ray direction and multiply it by the t indicates how far along the ray we have traced to hit that sphere. So what I want to do is I want to return the length of that. And that will be my distance. Okay, now we'll do something very similar for the plane. Okay, so again, the condition for solvability up here was the discriminant. The condition for solvability down here is the denominator, this expression here. So we get the t, that's fine. And now we have sort of two tests. We have, we want t to be positive, and then also we want this to be within the u and v bounds of the plane. So what I'm going to do is I'm actually going to put an early exit here. So I'm going to say if t is less than my threshold, then disregard it. And now I can continue here. So I just want to sort of reduce them. I know it doesn't really matter because if statements are always bad on shader code, but we'll do this anyway. Okay, just double checking. That's fine. So we don't need to do all this stuff with normalizing. All we really need is the same as above. And then if we get to this and we have not hit anything, then just return. Who cares? That's fine. Okay. So now fingers crossed for real. Let's see what this looks like. Okay, so this is pretty interesting. So clearly, yeah, things are pretty bright because I'm just adding a whole bunch of stuff. That's not great, but we can see shadows because for this large sphere, there's a bunch of other spheres which are kind of blocking different lights. Looks a little funky, but I mean, it's working. And if I if I updated this, yeah, some of this, I'll admit, some of this does look like an error. Like I don't know what's going on here, but it could be something that I haven't considered. Anyway, so yeah, but yeah, it's dynamic. So if I were to move the lights around, then these shadows would move as well, and we get it almost for free. Now, just note that there is some sort of error here. If I look at these, this yellow sphere from a certain distance, a bunch of pixels come up. That's sort of rounding errors in the cutoff that I put there. But anyway, in theory, this is working. And it took me a lot of experimentation to get that working, so I'm just going to kind of leave it as it is for now. Lighting. Okay, let's apply the lighting. I'm going to need a bunch of other directions as well. Once I've got this distance, I can normalize it. I'm also going to get the direction from the fragment to the viewer. And I'm going to compute the halfway vector for blend-fong lighting. Okay, let's start with the diffuse stuff. So the diffuse stuff is basically just taking the the normal of the fragment and dot product with the direction to the fragment, to the light, sorry. Okay, cool. So I'm squaring the distance to the light because we have quadratic distance fall off. And yeah, I'm taking the dot product of the normal with the direction to the light. So in a full reflective situation, the surface will be facing directly towards the light, and so that'll be maximized. Okay, let's go ahead and do that. Okay, so now things are starting to look a little bit more realistic. We still have some really weird, like, bright spots where the light just happens to be, I guess, right next to the edge of a sphere. That's fine. It comes down to the random number generator, I guess. And then, yeah, we have shadows and stuff. That's cool. Like I said, this is all real time, so this will, this would update. Okay, now we can add specular lighting. It's actually very similar. We just take the dot product of not the render state normal, but the halfway vector. This is the vector which changes according to the viewer's position. I've got a video on blend-fong lighting. Would definitely recommend checking that out. That's all looking good. But then to bring that to a single point, it's common to raise that up to a power. Power of, I'll go with 64. The higher this power is, the more concentrated it will be at a single point. Okay, so this is kind of looking a little better. If we look at this yellow sphere, then the lighting does whatever it does, but then as I come around, we get a specular component shining directly back at us. I feel like, Of course, I messed it up. Okay. All right, so redo. So we take the dot product of the surface is normal with the halfway vector, because if the light and the viewer are at the right position, then the vector between them will line up with the normal and we'll get like a full reflection. Okay, that's looking a little better. Now we have these little specular highlights, which depend on the camera's position, so it makes it look very sort of nice and reflective. We also have shadows. Here we can see a plane is casting a shadow on the sphere. Up above, we can see a sphere is casting a shadow on other spheres. Sometimes looks a little weird, but yeah, down below we can see a bunch of spheres casting shadows on each other. I'm pretty happy with how it is at the moment, and I'm kind of gonna leave it for there. Maybe experiment a little bit later. Okay, hope you enjoyed that. In the next session, I'm gonna have a look at doing a hybrid rasterizer and ray tracer. So I'm going to use deferred shading to capture the scene and sort of get the first approximation of the planes by rasterization, which is considerably faster. So it's almost like we get one bounce for free. Anyway, I hope you enjoyed this, and I'll see you again soon. Bye.